How's everyone feeling? You good? You coasting? When are your first finals? Monday? How many finals everyone has? 4? Okay, fun. Five. Almost there. All right. So today we're going to really briefly learn about random numbers, how we represent them on computers, and then we'll talk about using what we learned. Oh, I guess I should have had this pulled up. That's pretty close. Okay. Whenever you're ready, Katara.
So, chapter 10 was about making programs to pretty much generate random numbers. But the numbers that are being generated with these programs, they're determined through a formula known as a random number generator. So the numbers are technically not random. They only look random when they're generated, but that's also the deterministic formula that is mentioned as being used to generate them. So for equation 10.1, it's pretty much talking about how they use x to find x prime. And then below that is the details of the program that they use to generate it. The program calculates the first 100 numbers in the sequence that's being generated. And then on the next page, you see that plotted by a graph. And on that graph, the dots, they look random, which kind of solidifies the being the random number generator. Yeah, I believe for this program specifically, it's called the linear potential. I don't know if that's right.
Yeah, that's right.
Random number generator. It generates a string of random numbers and integrates that same equation over and over. And the book mentions that there's a few things to take note regarding it. The first thing is that, as mentioned before, the numbers aren't random. If we know the equations and the constants, then we're able to actually calculate the exact numbers that it would produce. And if we run the program twice, it would still give us the same output.
Yeah, so there's 2 pages missing here in the book. So hopefully you have the physical book because the online version doesn't have the pictures. I don't know why they're not copied here, but keep going. Yeah.
The second thing that it mentions to take note of is that the numbers are either going to be positive or zero, since they're calculated with modulo n. So they'll always be less than n, and all numbers are gonna be in between a range of 0 to -1. And further down, it just talks about how if you're wanting to change that scale or change the range, you can edit some things in the scale of it. And I believe that's why manipulating R. The third thing I want you to take note of is the values for the constants. They're chosen with consideration. So it's recommended to use the constants that were listed in the example.
And that's these ones right here. These are massive numbers, but they give you random numbers.
And then what's the called? It lets you know why it would be good to make certain choices. So if B and M were both chosen to be even, then it would only produce even numbers or maybe only odd numbers, but it wouldn't be able to be both. And then for number 4, it's saying that you could still get different sequences of random numbers by choosing different starting values for X, but you would still have to keep A, C, and M the same. And it mentions that the initial value that it produces is called a seed, which specifies where the sequence will start.
Yeah, so just to pause on that idea. So if you've ever played a game and you have to load a map in and it says loading random seed, that's what that means. So it literally is this idea that Keturah just talked about, which identifies what is the first value in that string of random values, because even though it's loading a random seed for you, potentially you're playing with other people, they are getting the same map, right? So therefore, all of your random strings should be the same. Does that make sense? Okay. So we talk about this idea of pseudo-randomness, which is it appears random because you will be unable to determine it just from looking at by eye, but the computer knows that it's not random. Okay, keep going.
That a version of the program that you can use that is straightforward. And it comes in a random package.
This is the next page we have, which is the 48, I think, or 84, sorry. 48. No worries.
This page mentions taking note of the random function, now the parentheses are empty, because even though it has no arguments, the parentheses are still required. And then it mentions that the functions are unusual functions in Python, and that they will return a new random number each time you use it. Like previous functions we have seen with assign and square root, it would return the same answer if you call it twice with the same argument. And then it lists that a little further down. And it mentions that the following code, that if you want to use the same random number twice in your program for 2 different things, then you would need to store it in a variable so that you can come back to it.
Yeah, so just to break that apart a little bit. So let's look at this first one. These are all provided by Python. This first one just gives you a random number between 0 and 1. And as long as you understand that that's any floating point number between 0 and 1, you can map that, of course, to any range that you want. But you don't have to, because you can get a random integer from here to here, or you can take that random integer and then you can change the width. You can divide it by whatever you want it divided by, etc. Right? So as Katura was saying before, if you print rand range 10, so rand range 10 says, give me a random integer from 0 to 9. So it should give you a random integer between them. The first one, it tells you 6. And if you type this in to your code, you will probably get 3 different numbers, right? That are different from the book, right? Okay. Whereas here, what is our expectation of what they will print after we assign Z to rand range 10? And then we ask it, that random number is Z, and we ask it to print that twice. What do we expect to get? Get the same number twice, right? That's really important. Okay, so to Katura's point earlier, if you want to use the same number, you assign it. So now Z means whatever this thing spat out. But if you just ask it to spit this out, it'll change every time. Okay? Oh, we don't have to go this far. We can just jump down to 11 now. Yeah, this is as far as I wanted to go. Because we're not going to be using, I mean, unless your code already requires it, right? But this is basically as what we need to know. I mean, you can go through and we can talk about drawing random number generators. But unless you're doing ciphers or Monte Carlo, I think only a few of you are doing those. And you probably are already using this. We could talk about the probability, like, you know, how to do a biased coin or how to use a flipping, right? So you create some random number and between 0 and 1. And if it's less than the probability that you're interested in, do one thing. If it's more, do something else, right? That's how you would do a random probability. But I think more importantly here, because we're not going to be doing these examples today, let's talk about the last. Can we talk about chapter 11? Is that okay? Okay, I'll talk about chapter 11. Okay, so let's go to using what we learned. Any questions for Katura before we move on? Yeah. All right. Cool. This doesn't cover all of computational physics. This barely scratches the surface. If you decide to continue in data analysis, you will need tools like interpolation, which is something we didn't get to. If you decide you want to go into modeling, you may want things like Markov chain Monte Carlo, which simulate walkers, and then they head off in a certain direction and you follow their path and you see where most of the people went, you know, so to speak. And so you find out what the most likely outcome is. We didn't fit any data. So there's a whole section that you could learn about that has to do with how we turn, you know, experimental data into some understanding of what we think the underlying parameters are, right? There's lots of fun things that you can do. We didn't really do any modeling of like fluids or boiling water, right? That's something that you can do on your computer. I mean, I know you can boil water at home, but once you understand fluid dynamics, you can simulate what happens inside of stars. You can simulate what happens in the ocean. You can simulate water, or sorry, I should say water, fluids going around a boat or like around a plane. So all of these things can be extremely lucrative when you think about the different ways that we can use a computer to understand the physical world around us, right? Can I make a slightly faster car, right? People like those things. Slightly more aerodynamic, perhaps, right? Okay. We talked a little bit about integrals. I think that this section is going to become less and less important as a function of time, you know? The hardest integrals to do are the ones that you can't do on the computer, but computers are getting really good at doing integrals. Linear systems of equations, these are great. They explain a lot of the mathematical world that we have been looking at. And linear algebra is annoying. You make mistakes, you write the wrong equations a bunch of times. So here, again, we're going to rely on computers to do that going forward. And then you have the two sections that I think are the most important. And the second one, or sorry, this third one here is finite element methods or finite difference methods. So this is how we represent differential equations. Like, for example, we saw how heat was propagating into the surface and how that changes with different time, right? Most people's projects, I think, in this room have to do with how time is changing, and then there are forces, right? So we almost always concern ourselves in physics with, okay, how does the object move under the forces of gravity or under the forces of electromagnetism or friction or something like that, right? And so similarly, this section, chapter 9, and of course, I think that goes into a little bit of chapter 10, those are really important to understand how to do well. There's many different ways and many different algorithms that introduce their own issues, right? They introduce approximation error. Numerical errors start to build up when you take small differences. So we want to be cognizant of all of those things as we continue to model physical systems, right? And then finally, we never got to it, but these are really cool. Monte Carlo simulations, they're essentially a way of measuring things statistically as opposed to modeling every single particle, right? Okay. Where's the, oh, okay, that's it. I'll just leave you with some final thoughts. Python is the future. Coding is not necessarily the future. I wouldn't have said this 5 years ago. I would have told you that every single one of you needs to learn how to code because it'll be the most important thing that you can do in undergrad. And yet, while I've been here, I haven't even been here 5 years, the world has changed dramatically. And the more important, the more valuable and more lucrative skill is not just knowing how to get the code, but as you hopefully have seen here, how to know if the code is right, right? What is the output giving you? And this kind of speaks to physics as a whole, which says, okay, I'm not just going to, sometimes, and no hate to engineers, but engineers really need to get the right answer so that the building doesn't break, right? And they really don't give a shit about the equation, right? You might say to yourself, well, I really give a shit about which equation I'm using and why. And maybe I really don't care that much about how right it is. It could be off by a factor 2 and you're still happy, right? You want to understand how the world works. They want to make sure the world doesn't break. So as we think about those in the context of physics and computational physics, right? You are experimenting with these tools. You're trying to understand how to break the computer. You're trying to understand how the code works. I hope that you find that that section of your learning, the critical thinking skills, will probably be more lucrative in a world in which computers can write code for you, right? So if you are not getting, if you're just out there looking for a job, you say, well, I'm really good at figuring out whether or not someone's debugged code is doing what I think it does, right? That's more valuable than being like, I can sit down and write 7,000 lines in an hour. You see? Make sense? Because computers can do that. Okay. If you go to grad school, if you decide not to go directly into industry, you'll need coding. You'll definitely need computational, unless you decide to do paper and pen. Or I guess you could build stuff. I don't know what building stuff is like. Legos maybe, but that's about it. And then if you decide to go into teaching, I hope that you teach students how to use code very early. This is fun. I try to incorporate a little bit of coding into all my classes. Sometimes it doesn't go over very well, but you'll see that especially as you get into sort of the upper divisions, it's like fun because you can take these equations, you have some differential equation, and you can right away just be like, oh, I know how to turn that differential equation into something I can do on my computer. So even though I can't think of what would happen, my computer might tell me, right? And that's pretty unique. Any other questions, comments, concerns? Okay, so that's all of the content that I wanted to go over. We can do an example of the random one if we want as a group, not for credit. I mean, if you want for credit, you can do it as for credit. But I don't want to force you to do something if you're sort of underwater with your project. Most important thing for me in the next day, right? Because there's no office hours tomorrow and your homework or your final project is due on Monday. Due on Monday. Does that make sense? Now, what does that mean? I still have office hours next week. So it's due on Monday. I need a version of it that you would be happy enough turning in. You hopefully are already writing or have started or finished your presentation. So you must have some results. Okay. So what I'm looking for then next week, you turn in the code on Monday before office hours. Because then I can look at your code and be like, oh, let's improve it in this way, that way, or this way, right? Okay. The final version of your code and your presentation will be due at the end of the week, Friday, close of business. Okay. So I can give you feedback if you get me a project that you're mostly comfortable with before then. Does that make sense? And I'll probably tell you your grade about that. Yeah. No, you're definitely presenting it. You're presenting it on Wednesday during class. Yeah. Hold on. Let's verify that. Well, we can do it on Monday. Who want to do it on Monday? Who want to do it today? No. Who want to like record a video and do it online? No, don't do that to me. Okay, so just to remember here, it's here. The final presentations are due in class on the 15th. Okay. And oh yeah, here's for anyone who didn't put their name in already, these are the slots. Alfred's going first in slot 3. Where do you want to be? Oops. Stop. I knew it. Embarrassment. Oh, and it's being recorded. Shit. All right. Is that everyone? 9. That's 9. What? Daniel and Jasmine. Okay. So we'll adjust that. Remember, as I said before, 7 minutes for presentation, a few minutes for questions. It has to be a minimum of 7 minutes. Yeah, per presentation. About 7 slides. I always say about a minute per slide. Yeah. Okay. And as we talked about before, the semester project is, of course, here on Canvas. Oh, it's not going to show up. Never mind. But you can look it up. It has all of the rubrics and whatnot in there. If you have questions, I'm happy to talk to you about them today. And if you also want to bring your presentation in on Monday and be like, hey, how does this look? Do you have any advice? And we can do that as well. So I'm having normal office hours Monday, Tuesday, and Wednesday. Wednesday's a little cutting it close, but no big deal. If I look at the math for this one, let's do a 1 p.m. start time. And then this will be about 10 minutes later. That didn't do anything. Oh my God. You know what I mean. Anyway, I'll do it later. Let's do it like this. Format, time. Yep. Stop it. Vaffanculo, Okay. How much of what is? Yeah, but why did it go so high? What is it doing? Look, okay, it's got hours. No, that would be very rude. Let's fucking go, boys. Okay. Figured it out. Okay. There we go. So 10 minutes. No, I don't have to go. Okay, so we should finish by like 12:30-ish. Right? Sorry, 2:30. So it's like an hour and a half. So don't get too sad. Come prepared. Okay. It's not stressful. It's just us, just friends. I won't record it. Okay. Questions, comments, concerns?
What time are you gonna have your office hours next week?
Same time as always.
So on Monday, all code is, when you say all code is due, that means like the pair programming homeworks and when you say like the final code for your final project. what's the difference with the due date compared to the due date on the 15th?
Okay, so I want your code submitted at the beginning of the day on Monday. So like 9 a.m. Okay. Now, can you still work on it? Yes. But do I want a copy of it? Yes. That is not all of your code. That is just your final project. Everything is due Friday at 5 p.m. Everything, right? But I'll still try to give you feedback. You know, the sooner you turn stuff in and I'm aware that it's turned in, the sooner I can give you feedback on it. Yeah. Next Friday. Yeah. Yeah. You have a little bit of time now, right? And that's why we're going to take the rest of this. I would ideally like you to focus on getting your project into a place where you feel comfortable turning it in Monday, right? That's the most important thing to me. And, you know, you want to do homework, you want to work on a pair programming, something like that. That's also an appropriate use of this time. Okay. Questions, comments, concerns? Break.